All right, we're about 4 after. Got quite a few attendees on today's call. It's obvious why we're talking about service mesh today. Thank you all for coming. Welcome to today's CNCF webinar, Simplifying Microservices Security with the Service Mesh. I'm Lee Calcote, CNCF Ambassador and Head of Technology Strategy at SolarWinds. I'll be moderating today's webinar. We would like to welcome our presenter today, our star, Neeraj Podar. He's the engineering lead at Aspen Mesh. I do have a few house cleaning items for us to walk through just in advance of Neeraj taking it away. Note that you're all here on our webinar, that you're all muted at the moment. We do highly encourage your questions. Please pop those into the Q&A at any time that you have a question. We'll likely take a break or two during Neeraj's presentation to answer your questions. So do find the Q&A box at the bottom of your screen. We'll get to as many of those as we can. Yes, before you ask, this session is being recorded, and the recording will be sent out along with a link to the presentation shortly after our call. With that, let's give a warm welcome to Neeraj Podar.
Thanks, Lee. Hello, everyone. I am Neeraj. I am the engineering lead at Aspen Mesh. Thank you for joining in on this webinar about simplifying microservices security with a service mesh. Before I begin, I would like to give a quick overview of how my presentation is structured so it's easy to follow along. First, I'm going to talk about why security is difficult in microservices as compared to monoliths, then move on to some of the key concepts of microservices security, authentication and authorization, then talk about how a service mesh can help you simplify it, especially taking Istio as an example, talk about Istio's architecture, then zoom back into the key concepts around authentication and authorization, take various architectural choices you have, both without a service mesh and with a service mesh. And then, like Lee said, in the end, we'll have some time for Q&A. So with that, let's get started. So security in general has always been difficult. It's even more difficult in microservices, as this illustration represents. We are no longer in the monoland or the monolith world as compared to microservices. When I think about microservices, there are 3 key things which are different that make the security even harder to implement. First, there is no single point of control. So in the monolith world, you had a single point of control where you could easily protect your perimeter. If you were protecting your ingress using a big IP or a firewall or Nginx, you were secure. When the request came to your monolith, now it was contained within that monolith, and more or less you were using process level interface or libraries to communicate with each other. Now you have broken apart your monolith, and now you have multiple microservices, and these microservices are talking to each other over network. They are using myriads of protocols and like HTTP, gRPC, Redis, Mongo. So you have just increased that complexity, and you have lost your strategic point of control. As a security person, you can see how this can be very difficult to manage. Moving on, most of the microservices are built using polyglot languages. What I mean by that is microservices encourage developers to write applications using languages that make it more efficient and that make it more easy to maintain. Naturally, that means you will have applications written in Java, Go, Node.js, Python. Now, if you're trying to implement security using libraries or using these frameworks, you can imagine the complexity as these languages keep on growing. Because you are embedding your security in the applications, first, how are you going to ensure uniformity across these languages? It's no longer a single language. It's no longer a single language that you can just implement a library and share across. Additionally, if you have a security patch, now you have to wait for that patch to be applied on all these frameworks. Traditionally, developers and operators and the security operators always had a strenuous relationship. It's kind of a love and hate where they both need each other, but at the same point, they hate each other because they might slow it down. They might slow their progress. Having polyglot applications and microservices just makes the relationship worse. The security people are more coupled to the developers if the application developer is responsible for enforcing security. Moving on, the third point is the increased surface area, which in a way is a combination of the first 2 points, but I like to mention it separately because it's beyond those 2 points. When you break apart a monolith into microservices, yes, you are increasing your surface area by the network calls they are making, by the different languages they are using. At the same time, now you're using different containers. Those containers come from different base images, which are all not in your control. Additionally, you might be deploying your containers and applications in environments where you might not be even controlling the nodes on which they are running. So all in all, this makes enforcing security in microservices a lot more challenging than what it used to be in monoliths. And that's why it's really important to understand how can you simplify your security landscape if you have a microservice architecture. So when we talk about key aspects of microservices security, I want to focus on 2 key things here, which are authentication and authorization. Authentication is the act of verifying or validating your end user or the client who is currently making a request. In microservices, sometimes it's actually the combination of both, because the client which is connecting to you might be a microservice in your network, but it might be making a request on behalf of an end user request that came in. So it's crucial to understand the complication that arises in the microservice world just for authentication. Normally, you will authenticate by creating a login and a password. Most of the modern applications delegate that to an identity management solution like Cognito, where the login password goes to Cognito, the AWS Cognito framework, for example, and the Cognito framework gives back a JART token or a JSON web token, where the applications are eventually presented that token from the end user, and that token acts as the identity. As the request moves along in the cluster, the token is the identity which verifies the user. So for the rest of this presentation, when we are focusing on authentication, I'm going to assume that this is the architecture that various applications are using, where a JSON web token or similar token-like architecture is what you have implemented. Authorization, on the other hand, is the act of verifying or validating if the end user or the client is allowed to make the request or has the right permissions to access the resource that they're trying to do. In a multi-tenant environment, if your application has multiple users or quality of services, normally you need some sort of authorization. And they both go hand in hand, but authorization is always the step which follows closely once you have authenticated the user. It's similar to saying if you have different roles, for example, you have admins, readers, and writers, then you want to know what actions they can or cannot do. So with that background, I want to make a statement here saying service mesh can simplify your security. At this point, this is just a statement. Hopefully by the end of the presentation, I have convinced you that this is the truth. In lack of service mesh, what you end up doing is to enforce authentication and authorization, you will write the logic in your applications, making them too complicated and coupling your operations and your developers team too close and too tightly. Service meshes can simplify security, and by simplifying, what I mean is it gives developers an opportunity to offload some of the functionality into the mesh. So let me give a quick background of what service meshes are. So service mesh is an infrastructure layer that handles communication between your microservices. As part of handling the communication between the microservices, it can offload the advanced traffic functionality and the security functionalities like authentication and authorization. So most of the service meshes work by adding a proxy, which will intercept traffic going in and out of your application. As part of intercepting the traffic, these proxies, which are not just parsing at layer 4, but they're parsing the application level protocols, they can implement the complex functionality of authentication or authorization as they understand these protocols much better. Depending on where and how you place your proxy, there are various architecture options that are available to you. And each of these options have benefits and disadvantages. One of the architecture options is a sidecar proxy deployment. And this is what the service mesh, which I'm going to use, Istio, uses. By a sidecar deployment model, what I mean is the Envoy proxy, the proxy which is used in Istio, is placed in the same pod as your application container is running. So in Kubernetes, if you're using Kubernetes, you have the concept of pods where you can have multiple containers. In Istio, the sidecar proxy will be placed inside the same pod, which means from outside, they look like the same network entity. They share the same networking namespace and the IP. Inside, they're still two separate containers. So they have separate file system and process level isolation. So this gives the right kind of isolation that you want and uniformity for the network, where you can have the application container built and deployed separately and the proxy have its own build lifecycle. So normally in Istio, what that means is when the application makes a request out, it will be intercepted by the sidecars here shown in pink. Then the sidecar is eventually going to make a request out to the other container, in which the request will again be intercepted by the sidecar container and then eventually forwarded onto the application. The same path is going to be followed for the reverse side when the response is made. All the sidecars together are what we call the data plane of the Istio architecture. Istio has a nice separation between the control plane and the data plane. The control plane here is shown in blue at the top. The control plane is responsible for configuring the Envoy and the data plane proxies. At the same time, it is responsible for providing an abstraction layer from the data plane. The control plane itself in Istio is distributed. So the control plane has various components which can independently scale, and you can upgrade them depending on the requirement. Similarly, having a decoupling between the control plane and the data plane gives you the ability to independently scale and upgrade them. So I'm going to quickly go over some of the key control plane elements here so that we can use them later in my presentation. So first is Pilot. Pilot's job is to provide an abstraction layer for the configuration. So it looks at your platform specific configuration. So if you're using Kubernetes, it will look at services, endpoints, pods, and then lower it to the configuration that Envoy understands. Similarly, Pilot also consumes all the Istio level configuration and lowers it to Envoy. This provides the benefit to the operators where they can use their platform specific configuration and APIs and don't have to worry about Envoy APIs. Second is Mixer. Mixer provides two key functionalities. One is Mixer provides one form of policy enforcement. We'll talk in detail later how that works. The second is it provides a layer for telemetry abstraction where your sidecars or the data plane can export statistics and tracing, for example, in some format, but Mixer can transpose this and add as an adapter layer where you can eventually send that data to a backend system like Prometheus or a Google Stack driver. So in this way, again, there's an abstraction between what the data plane can do and what the control plane supports. Citadel is the control plane element responsible for creating certificates and rotating certificates on a regular cadence. So in Istio, if you are using functionality like mutual TLS, which I'm going to cover in details, Citadel is the component which will create these certificates and present them to the Envoy sidecar. Traditionally, Citadel always used the platform specific mechanism. So it will use things like Kubernetes secrets, and those secrets will be mounted on the file system. But from Istio 1.1 release going forward, Citadel provides implementation for the secret discovery service or the SDS API, which now Envoys can consume directly to get those secrets. And this makes it more secure so that the secrets or your certificates and keys are never exposed on the file system, reducing yet another vector of attack. The sidecar injectors are a Kubernetes specific control plane element, which are responsible for injecting the sidecars automatically when the pods are coming up. This makes sure that you don't have security escapes if you're relying on Istio for enforcing them, where some pods may or may not have sidecars. The last two components are the ingress gateway and the egress gateway. The ingress gateway is responsible for letting traffic into your mesh, and the egress gateway can be used for controlling traffic out of your mesh. So with that background, I would like to now zoom in into one of the key concepts for security, which is authentication, and then see how what options you have for verifying them. I think this might be a good point for some Q&A if Lee, there are some questions coming in.
I'm going to interject there and just say that we don't have any outstanding questions at the moment. So this is a good time to do two things. One is to encourage our attendees to ask those burning questions. So see your Q&A panel below, ask your questions. Also, we may have a poll for you. So if you see a poll pop up, be on the lookout for that. We're curious as to where people are in their journeys with Service Mesh. So with that, maybe we'll back to you, Neeraj, more on authentication.
All right, thank you, Lee. Oh, I did just see a question pop in.
And there we go. Oh, we got a couple coming through.
All right. Lee, you wanna?
Yeah, if I could. So, you know, question from one of the questions here, if I get it correctly, and that's, you know, it sounds like probably in contrast to Kubernetes, and I'm interpreting the question here. So in contrast to Kubernetes, how does Istio's RBAC and kind of admission controller, some of these overlapping concepts differ?
Oh, that's a great question. And I have a separate section in my presentation just for authorization and Istio RBAC. So let me revisit this. And if by the end of that section, this question is still unanswered, I'll be more than happy to elaborate.
Very good. One other question has just rolled through, and that is, can you explain again the security part of Citadel, the certificate authority?
Absolutely. So Citadel is responsible for creating certificates for the data plane or the Envoy proxy when you have mutual TLS enabled. So normally when you have MTLS enabled, you have to manage certificates for both the client and the server side. Normally this is quite painful to do on your own. You have to keep rotating them. So Citadel will create those certificates with the identities that I'm going to talk about later. Additionally, Citadel is now exposing a secret discovery service API, which is a new API that Envoy had added, which allows you to fetch those certificates and secrets directly. So you don't have to mount those certificates on the file system. And because you're no longer mounting them in your file system, you are reducing your vector for attacks.
Very good. Yeah. Thank you, Neeraj. Those are all the questions that we have right now.
All right. Thanks, Lee. Let me continue on to authentication, and we will elaborate. We're going to talk more about Citadel as we go along. All right. So as I was saying, I'm going to assume that you are using some sort of token. In this case, I'm going to assume you're using JWT tokens in your applications to validate the end user. So this is the first option you can have in your applications, where the application itself is validating the JAR token. So here we have two applications, or two microservices, I should say. You have user service written in Go, and you have your payment service written in Python. So the end user is making a request, which comes to your ingress. The request is encrypted, and it has a JSON web token in it as the authorization header. The ingress will do the termination for those requests. So that means normally this is the format I have seen which many users and many organizations have. Ingress is the TLS termination point. So going forward, what that means is ingress is then going to forward those requests to the services based on paths, for example. So here If it is a /user, it goes to the user service. If it is /payments, it goes to the payment service. So what that means is the request which contains the JART token in authorization header is passed in plain text from ingress to the backend, and then the backend uses some sort of library to validate the JART token, and then if the request is valid, it actually processes it. If it is invalid, then it sends a authentication rejected response to the client. So there are two problems that happens if you implement this architecture. First is, as you can see, the link between the ingress and the backend is unencrypted. That means you are opening yourself to replay attacks, as anyone who is eavesdropping on the network can capture the JART token and assume the identity of the end user. Second, you are using application code to implement this validation. That means you will have to periodically fetch, or at a startup, fetch the JART, fetch the public key from your identity management solution. At the same time, if you have to swap out the identity management solution, you have to change all the libraries, which, like I was saying, makes the coupling between the security team and the developers really close together. So that's the first option, less than ideal. Let's move on to the second option, which is also I've seen many companies implement, which is I'm going to move my logic of validating JART at my application to the ingress layer. So in this case, what happens is the ingress is responsible for communicating with the identity management solution and then only passing along the authenticated request to the backend. So you have done one thing, you have offloaded some of the functionality to your infrastructure. That's good, but at the same time, you still have two outstanding issues. First is the request that comes from the ingress to the backend is still coming in plain text. So that means you're still open to replay attacks. Second, in most of the microservice architectures that I have seen, you will have a nested flow of calls. So the payment service is going to call another service like banking, and most of the time, you will be doing a propagation of the identity. So you will propagate the JART from payments to banking. But again, you don't have any encryption between services in your cluster. So you have exposed or increased the surface area for replay attacks. Every hop where you're propagating your JART, you are potentially opening yourself to some security vulnerabilities. So two options, less than ideal. So let's see what Istio can do and how Istio can simplify this for you. So these are the next two options that I'm presenting. First is, in Istio, you have the capability of configuring your sidecars or your ingress to do JART validation. So by configuration, you can say which sidecar or a service for which the sidecar is attached, you can do JART validation at that point. Additionally, in Istio, you can configure the functionality you want your ingress to do. So in this architecture, we will say, we'll configure our ingress to do TLS pass-through. So in this case, the traffic comes encrypted to the ingress. Ingress will do SNI, or server name indication based routing. So it will look at the host which is presented in TLS during the TLS negotiation and use that host to do the routing. So instead of using, if you see /users and /payments, now you have to do domain based routing. Then those requests are eventually given to the sidecars. The sidecars are configured to do JART validation. So what that means is, in this case, pilot gets your configuration from the operators. So that configuration has things like JART URL and various other JART attributes. It fetches the public key from the identity management system and it configures the sidecars with that public key. When the sidecar receives the request, it uses that public key to validate the JART token. If the token is valid, if the signature is valid, it will forward the entire token to the backend. If the token is not valid, the request is rejected. So this has two benefits. First is the backend only receives the token when the JART is actually valid, or it only receives the request, I should say, when the token is valid. Secondly, you have encryption from ingress to your backend, but it also has some downsides. particularly because you are using domain-based routing, you lose some of the advanced capabilities around path-based routing. So you have restricted what the ingress can do. Secondly, because still you're not attaching identities to each microservice, when the sidecar, when the application is trying to propagate the JART headers, so in this case, when payments is trying to talk to the banking service, still you don't have encryption in that link, and you are still exposing yourself to replay attacks. Note that one thing is important here, where the Istio sidecars by default will only propagate JART headers one hop. That means if the request is made from ingress to the payment service, the sidecars will decode the JART or verify the JART, send the JART token to the payments backend service, and when the payment service is making a request out to the banking service, it has to reissue or it has to include the JART header again. So you can see there are some benefits of this architecture, but also you're losing out a lot. So this is where I wanna stress on the fourth option, which I think is the most secure option, which is using Istio MTLS plus JART validation. So Istio has the capability of issuing identities to every service in your cluster, and those identities will be unique to each service. Using these cryptographic identities, you can secure traffic at each hop. So in this example, what that will mean is the user's traffic is presented to the ingress encrypted. The ingress or the Istio ingress will terminate that traffic. Then the ingress will re-encrypt the traffic with mutual TLS with its own identity and the identity of the sidecar for the user service or the identity of the sidecar for the payment service. So you have encrypted traffic on these links. Then you can configure the sidecars to do JART validation. So in this case, you will say user service and the payment service will do JART validation. And then if the payment service wants to communicate to the banking service, it can propagate the JART, but because you have MTLS between those links, you're never leaking your JART token in open. This is a drastic improvement as compared to any other solutions that we have talked before, because every other solution had holes where somewhere or the other you were leaking your JART. Additionally, in this case, Citadel, like I was explaining before, is responsible for creating those certificates which will be used for MTLS and automatically rotating them. So not only are you delegating your JART validation, but you're also getting MTLS without the overhead of managing certificates for you. So this for me is the most secure implementation for doing authentication for services at the same time without taking on the burden of doing it yourself in the application. So next, I have a simple example of how you can actually do this in Istio. So if you want to configure Istio MTLS plus JART, here are the things that you need to configure. First, you will need to configure mesh policy. So here, as it says, this is a default mesh policy, which is turning on MTLS for the entire cluster. So note that when you create mesh policy or authentication policies, you're only configuring the server side. For configuring MTLS, you need to configure both the server and the client sides. The client side configuration is done by configuring what we call destination rules. So this is a default destination rule, which says for any host ending in star.local, so that means for any host or services that you're communicating to within your cluster, within your Kubernetes cluster, you always use Istio mutual. So this is one area where I've often found the first time users in Istio tripping over because they're confused as I have enabled MTLS policy by mesh policy, but it doesn't work. So you need both the sides. Secondly, when you want to add JART for specific services. So for this example, if I wanted to add JART for HTTP bin service, this is how I would do it. I'll create an authentication policy, which will target a name, HTTP bin. This is the name of the Kubernetes service. And it is important that you can only use short names over here. Istio will automatically create fully qualified domain names based on the namespace you're creating this resource. So there are two important things to note. First, you're creating a JART section here, which will say what's the issuer. You can also say what is the URI from where you want to fetch your public keys. Secondly, it is very important to always specify MTLS here. So any policy that you write will always override the default policy. So in this case, if you skip specifying MTLS, what will happen is the server side will be configured to just use JART, but the client side will be using MTLS. So this is another one of the reasons people have difficulty using Istio when they first start out, as they create the default mesh policy, but when they create override policies, they forget to add MTLS. So hopefully this example helps you in understanding what are the pieces you need if you have both MTLS and JART enabled and offloaded to Istio. So next, I want to show how the policies or the configurations are actually lowered from Istio specific configuration to Envoy. So for most of the cases, you don't care about this if everything is working correctly. But for debugging, this is really helpful to understand how is the config eventually given to Envoy and what actions does Envoy take. So if you have configured JART, as you can see, Pilot will automatically go and fetch the public key and set the JART filter for Envoy, saying these are the keys you should use for inline validation, and then forward the request to the application container. It is also configured to use MTLS on the server side, as you can see. And then there are a few things like what's the principal binding. Those are used mostly for some sort of attribute matching and generation. Next is when you create MTLS, configuration by default or for some services in your cluster, like I was saying, Istio will attach identities for every service. These identities are based on SPIFFE specification. So this is what we call a SVID or a SPIFFE verifiable identification document. So Citadel automatically creates these certificates which have a subject alternate name with this SPIFFE spec, and the sidecars are configured by Pilot to verify that the SAN presented from the other side honors or meets this criteria. So for this example, whenever Envoy is trying to reach out to this cluster http bin.foo, it will use this. It will verify that the subject name matches this criteria. And this SPIFFE specification is built around the domain, which is cluster.local, then the namespace, and then the service account that is attached to the workload. So these are some of the examples of how you can use Istio to offload authentication, and then look at your Envoy configuration if you want to verify that actually you are doing what you have configured. So with that, I'm going to ask Lee if there are a few more questions, and this is a good time to answer them.
Yeah, we got a couple here, so let me see if I can get them correct. One of those is with respect to authorization, which we're about to dig into, and so maybe you'll answer this going forward. But the question is, in this case, authorization, or rather, I guess I'll read it. In this case, authorization is done by, what happens if authorization is done by the actual service and not by the sidecar? That's the question.
So great, that's a great question. So the first thing that I tackled is authentication. So if you just want authentication to be done by the sidecars, you can do so, in which case, if the request is correctly authenticated, the service will get the request and the service can do the authorization by itself. The next section that I'm going to cover explains how you can offload the authorization functionality also to the mesh, but Istio by default is always additive and incremental. So if you have built some of the logic in your application, you don't have to remove it. You can add Istio and gain some functionality, and then eventually move things out of your application if you want.
Very good. A second question was, really, I'll summarize, but it was a recognition that the link between pilot and the identity management service, or the box that you had in your diagram, given that that's out of Istio's control, what's to prevent eavesdropping from happening there? That was the question.
So, I mean, I'm assuming whatever link you are using for getting the public keys are encrypted. So if it is encrypted, you should not have any eavesdropping.
Very good. Third question. It seems MTLS is only supported in service-to-service traffic. Is it possible to enable MTLS for pod-to-pod communication?
So maybe this is clarification in terminologies. So whenever we're talking about service, service itself is an abstract concept in Kubernetes. Eventually, it's the pod which are communicating to each other. So traffic between pods will be by default encrypted when I say service to service encryption. Now the traffic between the application container and the sidecar container is mostly in plain text, but that's a different story.
Very good. Okay. And then actually maybe we'll wait to the end to talk about our poll results.
Absolutely. Sounds good, Lee. All right, so let's move on to authorization. So like I was saying, authorization is verifying whether the user or the client who is connected to you is allowed to do certain actions. So normally you do this by either having role association where roles are tied to actions, and then a user comes in and they can assume a role or they're part of a group like admin, reader, or writer, which is called RBAC. There's a second form of access control, which is attribute-based access control. I think of this as a little more complex but more flexible access control mechanism where you have policy framework and a policy language set up, and you have set of attributes. Those attributes can be tied to resources, to users, or anything else. And then you're doing complex Boolean arithmetic kind of a thing to determine if a particular user request is allowed to go through or not. For most of the cases, RBAC works well and it is good enough, but in certain cases, you might need ABAC. So just like the authentication mechanism, you can do all the authorization in your application. Istio out of the box provides both RBAC and ABAC. So this is how Istio RBAC works. So the operator will configure Istio policies, pilot watches for them from the Kubernetes API server, and distributes the appropriate RBAC and RBAC characteristics or the RBAC rules to sidecar, which enforces them. Istio by default will do two kinds of authorization. One is service to service, and the second one is end user to service. Just like authentication, it's important in microservices to do both. You can have one service talking to another service and you want to know what it can or cannot do. Additionally, you have the end user who is making requests, and then you want to know what is the end user allowed to make requests to. Is it allowed to delete collection? Is it allowed to read? Is it allowed to write? So this is a simplified example of how you can enable Istio RBAC service to service. So remember, whenever you're doing RBAC, you have to have MTLS enabled. Like I was saying before, authorization only comes in after authentication. And for authorization to make sense in Istio, the services themselves need to have identities, which is what MTLS gives you. If you don't have an identity, you won't be able to authorize them. So for configuring RBAC, first you need to do is enable a cluster RBAC config, which tells you which namespace or all namespaces you want to include or exclude. So this is a way of incrementally adding authorization in your cluster so that you don't turn it on and then everything stops working, which is also some of the things that users have difficulty with when they add Istio. So I'll always recommend add authorization incrementally. So when you add authorization, the next step is to define your role and role bindings. So a service role is akin to any kind of role which you can define in Kubernetes or you can define elsewhere. So a role tells you what are the actions you're allowed to make. So in this case, this service role is telling that it is allowed to do a GET request for any service, provided the constraints are the destination application label has to be one of the product page details, reviews, or ratings. So Istio has a very flexible way of defining the constraints where you can give it access to, in this example, even though the access is given to all the services by star, you're constraining them by some other properties. Next is a service role binding, which is similar to how a Kubernetes role binding works. Binding binds a particular role, in this case, a service role, to a set of identities. The identities are the principals or the subjects who are allowed to take these actions. So in this case, we are creating a viewer service role binding, which binds the service role to the subject, and the subjects in this case are, if it's a service which is presenting with the source namespace of Istio system or the source namespace of default, it is allowed to make GET requests to these pods. So basically, at the end of this setup, you have created a system where you are restricting who can talk to what, and all of this is done in the mesh where the application container itself will only get the request once the sidecar allows it to go through. So this is an example of, if you have that configuration, what your Envoy configuration will look like. Remember, Pilot will take all the resources that you define here, lower it down and send it to Envoy. In this case, it invokes an Envoy RBAC filter, which you see in the top. And this might look like a lot of policies and crazy JSON, but it actually works very well. And more than that, you are not configuring this. That's the beauty of Istio. You are actually configuring this. So what this is telling you is there are a set of principals that are allowed to make the request, and the principals have to have these regexes. And this is matching what you did in the earlier slide. So next, let's move on to when you want to do authorization from end user to services. So this is if the end user has a JART token. Normally you have some claims stored in the JART, and you want the services to enforce RBAC based on those JARTs. Again, you can do this in your application, but you can also use Istio configuration to handle this for you. So for enabling a RBAC from end user to service, it's a little more complex, but this is what you need. First, you will need an authentication policy. So in this case, there is an authentication policy just like before, which has two things. It needs to have MTLS and it needs to have a section for JART. Then you have your cluster RBAC config, which is included for some namespace. You have your service role like before. The next thing is you'll create a binding. And in this case, the binding is different than your earlier service role binding. So this binding, instead of using the subject for source namespace, you are going to use claims directly from the JART. So in this case, it is saying, if the JART that is presented is showing that it is part of the group 1, it is allowed to assume the role of HTTP bin viewer. So on the right side, you're seeing a JART payload, which will actually work for this configuration. So if your JART payload has groups, group 1 and group 2, this request will make it to the application. So this is a very simple way of making sure that your applications never get requests which are neither authenticated nor unauthorized. And you can assume that all the requests that are coming to your application container are ready to go or good to go. So if you do this kind of an operation, this is what your Envoy config will eventually look like. So in this, if you see, your principals are now saying it should match one of group 1, and the path is from the request auth claims. So even though I've given you an example of group, if your JART has some different fields, for example, scope, you can use any arbitrary fields from the JART token and use it for authorization. The next thing which I'm going to cover is the Istio attribute-based access control. So the former concept was Istio RBAC. Istio also provides a more expressive yet more complicated attribute-based access control. So the way that works is whenever a request reaches a sidecar, before the sidecar forwards the request to the application container, it makes a check call to the mixer. During this check call, the sidecar forwards various attributes of the request. So it will forward where the client is, where the server is, what are the request parameters like the method, URL, size, and then mixer takes in various Istio configuration and has an adapter API where it can invoke any third-party adapters for enforcing those check calls and running policies on them. So in this case, you can add an open policy agent adapter, which is a flexible policy framework which Istio provides. If you want to use, some of the organizations are already using OPA for enforcing policy in other parts of the system. So this gives you the flexibility of using a uniform policy language. So the OPA engine in this example will run the policy against the attributes that you have given and make the decision yes or no, send the decision back to the sidecar, and then the sidecar will enforce it. So if the decision is yes, it will forward the request to the user service or the payment service. If the decision is no, it will reject it. As you can see, there are some problems that might happen if you use this mechanism. One is because the sidecar is making out of process calls to the mixer, you can have additional latency. Obviously, if you make that call for every request, this system is not tenable. Istio provides a caching mechanism where the sidecar stores the results of the policy checks, and if this based on attributes. So if your request arrives with the same attributes, your cache is hit and you don't have to make that call. Again, from where I stand and what I have seen, most of the users only need the Istio RBAC, and they are good with doing that. But if you need some more advanced functionality, there's always Istio ABAC. So this is just, in my opinion, the tip of the iceberg. There are a lot of complicated things you can do with Istio by combining authentication and authorization. So some applications I know have systems where they have JART-based authentication, but then they also have a separate database where they are doing authorization. So in that case, you can have a middle layer where that layer can get the authorization tokens or authorization claims from the authorization DB, re-encode it in a JART, and then use the JART going forward and start enforcing. So basically you can have a user level JART that is presented by the user, but once it reaches in your cluster, you can convert it into a different JART, for example. So the last thing that I want to talk about is a zero trust network. And basically what I want to say is, this is a concept and terminology that is often thrown around in the microservices world. It is based on the principle of trust nothing, but verify everything. So basically what you want to do is, even if the request originates from within your network or within the parameter of your organization, you don't assume that you can trust it, but you want to verify it based on what the credentials are. It's easier said than done, especially if you're doing this in your own applications. This is where I think the real benefit of Istio and a service mesh is. You can use Istio to attain the principles of zero trust easily by doing things like MTLS, which is making sure that now you have identities and encryption for all network traffic. You can enable certificate rotation, which makes it more secure, which otherwise is again difficult to do. You can add auditing and logging by just storing all your requests in the form of traces, which are another one of the requirements of a zero trust network. Additionally, you can implement the features and the capabilities of a zero trust or capabilities of principle of least privileges by adding RBAC policies, again, all in Istio or a service mesh without doing it in applications. So for me, this is where the real benefit comes in. If you are looking to move to a more secure environment in microservices, you can use a service mesh like Istio to go there without baking all of that application, baking all of the complicated logic in your applications. So with that, let's move on to questions.
All right, very good. That was a well done presentation, Neeraj. Thanks.
Thank you.
We do have an outstanding question, and I encourage others to come in. There's a question here with respect to MTLS, and it's about configuration of destination rules. Within a destination rule, there's a configuration item, the host attribute. Normally within there, that host attribute accepts a service name. So the question is, how do you configure the client being the sidecar proxy client, to enable MTLS to a specific destination pod? And so if that makes sense.
I think I get the gist, and thank you for this question. And this is one of the real difficult issues with Istio related to the APIs. So when you are configuring destination rules, you're configuring the client side. The way you're configuring the client side, you're saying, whenever you're talking to this service via host name, you want to use these configuration parameters. So that will be enforced at the client side proxy. When you're configuring authentication policy or MTA or mesh policy, those things will be enforced at the server side. So even though you are not using client workload by name, because of using the host name, whenever any request is invoked with that host name, automatically that configuration will take effect on the client side.
Okay, very good. Very good. Another question here. What is the area of work or focus for Aspen Mesh?
Oh, thank you. So we are a supported enterprise-grade service mesh built on Istio. So we help companies which are navigating through the microservices journey, help them simplify their architecture by easily adopting a service mesh. So we provide support for them. We have a hosted SaaS platform, which lets you easily configure and visualize the things that are happening in your cluster. At the same time, we provide some advanced analytics based on the metrics and configuration that we gather from your cluster, which can alert you and tell you about things that are going wrong. So it's a combination of things which gives you benefits around security, observability, and support, which is a built-on capability on the open source Istio.
Oh, very good. Is that, is it aspenmesh.io?
Yes, it is. It has to be.
Very good. Those are all of the questions that our attendees have asked so far. I suspect there may be a couple of others out there. We did push out a poll that all of the attendees have answered, so thank you for that. Maybe we can review the answers to the poll. So the poll question was, are you using a service mesh today? And what we've found here is that 61% of our attendees are not yet using a service mesh. 25% are experimenting, and 14% are running a service mesh in production.
Oh, wow.
That's insightful.
Oh, that's very helpful. Especially, I mean, it's such a new technology that I think there's a eventual curve to adoption. So I'm really excited that more and more companies and people are trying it out. And please give your feedback, not just to Aspen Mesh, but to the open source community so we can help improve it.
Totally. I think we're nearing the end of our time. We've got a couple other questions. So just a reminder, there's a couple of questions about the recording of the recording of this webinar and the link to the slides. They will be sent out in email very shortly. One of the other questions here is, can you use Aspen Mesh to secure communications with services running in non-containerized workloads outside of Kubernetes?
Absolutely. I think that is one of the things that as an enterprise supported service mesh, we are trying to simplify. So the open source service mesh itself allows you to bring VMs or use things like configure things that are not running in your containerized environment, but Aspen Mesh can make that journey simpler for you. So just to give a background on Aspen Mesh, we are an incubation out of F5 networks. So we have the pedigree of working with enterprises with the legacy applications. So we know how that works and we can make it easier for you to adopt.
Very good. Okay, we've got a request to squeeze in one more question here. And that was just going back to the question about kind of Kubernetes RBAC versus Istio RBAC and kind of admission controllers within Kubernetes versus Istio.
I see. So in Kubernetes, when you're defining RBAC, you are defining what users can do or cannot do with related to the Kubernetes API server and the Kubernetes resources. In Kubernetes, you're not defining RBAC for service-to-service communication. In Istio, that's what you are defining. So even though the terminologies overlap, the aim and the intent is quite different. What was the second part you asked, Lee?
It was with respect to admission controllers.
I see. So admission controllers are, again, a way of making sure. So there are numerous types of admission controllers. In Istio itself, you have the sidecar injector, which is a validating and a mutating admission webhook. So admission webhooks or controllers makes sure that your configuration that you're applying is correct. As part of the admission controllers, also you can have authorization. But again, that is orthogonal to how traffic flows. So Istio comes in after you have configured your things in Kubernetes. Istio is when traffic is flowing through your system.
Very good. I suspect we could take questions for quite some more time. Certainly a hot topic, certainly a hot company as well, Aspen Mesh. So, with that, just a reminder, Taylor did post the link to where the recording will be and the slides will be. We're a little bit over the hour, so unfortunately we do need to wrap up. I do want to thank Neeraj very much for today's presentation, very informative. Thank you all for joining. We'll see you on the next webinar.